Here are the answers to the multiple choice quiz on stoichiometry and limiting reactants. I love these particle model questions, and the AP test is kind of obsessed with this stuff because it's just good chemistry. Do you understand on a particle level what's happening? I mean, not just can you plug a bunch of stuff in your calculator. Although sometimes this bothers people where they're like, I just don't even know what to do. So the key is that we have to look at the ratio from the balanced equation. I need 1 nitrogen for every 3 hydrogen, and when I find that ratio, I will produce 2 ammonia. So here's what I like to do. I like to just kind of group the particles as much as I can according to the ratio in the balanced equation. So the nitrogen are the white atoms and the hydrogen are the black. So I'm going to look for a group of 1 nitrogen and 3 hydrogen, for example. And every time I can group those particles together, I'll produce 2 ammonia. So this group will give me 2 NH3s. And then I just do that as many times as I can. So there's 1 more nitrogen. So I could group this nitrogen and give them 3 hydrogen. And that grouping will produce 2 ammonia. But now I'm done. That's as far as I can go because I ran out of nitrogen, which now we know that we would call nitrogen our limiting reactant, right? And then whatever's left over is our excess reactant. So I should be able to produce a total of 4 ammonia, but do you see these little boogers left down here? There are 3 hydrogen left over. That's the excess reactant. And so it's important to know that they're still there. So when I show my particle model, I show any products that are formed and anything excess that is still left over. Total of 4 ammonia and 3 hydrogen left over. Okay, so now we get into stoichiometry, and you think, gosh, how am I ever going to be able to do stoichiometry without a calculator, right? When we do the multiple choice on the AP test in May, we do not get a calculator. But the numbers they give you are going to be manageable. And the point, too, is just, do you understand your answer? Is it a reasonable answer? Do you understand the process? Not, do I have to plug everything in my calculator? So here I have about 63.2 grams of potassium chlorate with a molar mass of 122.55 grams per mole. That's not an accident, because just by inspection, I can kind of tell that I have, about half a mole? The potassium chlorate decomposes, and we want to know how many moles of oxygen are formed. So you got to set it up. So when I'm taking the test, I'm going to need some scratch paper, and I'm going to write this blue stuff so that I set up my stoichiometry. I start with the amount of potassium chlorate that I have. Because it's in grams, I have to get it out of grams. So I got to cancel grams so I can get it into moles. And right there I notice that I'm going to be about half a mole. And I keep going with my stoichiometry. I'm at moles of potassium chlorate, which I now want to cancel and switch it into moles of oxygen. And at the end there, when I'm converting between moles of different substances, I just need the ratio in the balanced equation. Oh, well, there's only going to be one answer that's even reasonable. So I've got about half a mole of potassium chlorate. Half a mole times 3 is what, like 1.5 divided by 2. I'm looking for like 0.7 something. And there's only one choice that's even close. So you just got to be able to set it up and then use your noggin a little bit. The numbers are meant to be manageable. Same thing with this one. They give me a balanced equation, which they'll often do in a multiple choice question. Often, not always. But sometimes they'll give you the balanced equation so that if you get the question wrong, it's not because I wrote a formula wrong or because I balanced wrong. I mean, sometimes if they don't give you an equation, it might be something really simple that we're just not going to get wrong. But here I have the equation, and I want to know what mass of carbon tetrachloride is formed by the reaction of 8 grams of methane with excess chlorine. Okay, so excess chlorine means I don't have to worry about a limiting excess situation. I know that the 8 grams of methane, CH4, that's going to be my limiting because they tell me that the chlorine is already in excess. So I'm going to switch between the methane, CH4, and the product, carbon tetrachloride. Alrighty, so we got to get those 8 grams of methane into moles. But shocker, if you estimate masses on the periodic table, which obviously you're going to do when this is multiple choice, you're totally going to round and estimate. Yeah, CH4 is like 12 and 4. It's 16 grams. And I've got 8 grams. I have half a mole. Then I look at my ratio in the balanced equation. It's a 1-to-1 ratio between the methane and the carbon tetrachloride. So I'm going to get half a mole of carbon tetrachloride. Which then, to get this guy, I just estimated on my periodic table. I mean, the chlorines are each about 35.5-ish. I multiplied that times about 4, and I totally estimated and rounded, added a carbon in there, and got about 152. So I'm looking for about half of 152. Is that like 70 something? There's only one choice that's reasonable. So you don't have to like plug this in your calculator to get the final answer. Once you set it up and you kind of eyeball it, you look for the answer that's reasonable. Fantastic. I like that one. Number 4, hydrogen reacts with oxygen to produce water vapor. Now here might be an example of an equation that maybe they wouldn't give us because this is pretty simple, but they do, and it's balanced, which is great. I have 6 grams of hydrogen reacting with 32 grams of oxygen in an explosion. The final gas mixture will contain how many total moles? And that's usually the part of this that we miss if you got it wrong. How many total moles are present after this reaction occurs? Okay, so again, these numbers aren't accidental. I have 3 grams of H2 hydrogen, or 6 grams of hydrogen. And when you're calculating moles, if it's a diatomic particle, I do need to use the mass times 2. So when I look at the periodic table on a multiple choice, I'm saying that hydrogen's mass is 1. And so that H2 is approximately 2 grams per mole. I've got 6 grams, so that's 3 moles. Oxygen's mass is like 16. The diatomic, the molar mass is about 32 grams per mole, and I have 32 grams. So I've got 1 mole. Okay, that is not the ratio from the balanced equation. For every 1 mole of oxygen, I only need 2 moles of hydrogen. I have 3. These amounts are what you have. It's using the amounts that are given. That's what I have. But I only need 2 hydrogen. Okay, so that's going to make hydrogen my excess. So then oxygen is my limiting. You could also think of it backwards. For every 2 moles of hydrogen, I only need 1 oxygen. I need half as much oxygen. So if I really want to react 3 moles of hydrogen, I need 1.5 moles of oxygen, and I don't have that much. Oh. So then with my 1 mole of oxygen, my limiting reactant, I can make 2 water, and of course 2 is one of the choices. But if you picked 2 and you got it wrong, I bet you just forgot about this guy. Yep, there's going to be 2 water produced, but we only need 2 hydrogen and we have 3, so there'll be 1 extra mole of hydrogen left over. So when the question says something about like how many total moles after a reaction, it'll be anything produced plus anything left over. Tricky, huh? All right. Oh my gosh. So this one is a little bit annoying. And I didn't show all of my work, but maybe you did. Hydrogen reacts with nitrogen to produce ammonia, which they give me the equation. Fantastic. Which of the following reaction mixtures would produce the greatest amount of product, assuming all reactions went to completion? Okay, so you have really no great option here, but you kind of have to inspect each of the 4 choices. All right, so I took the first one. 2 moles of nitrogen and 4 hydrogen. So if I look at the balanced equation, if I maybe start with my nitrogen. If I start with my nitrogen, I need 3 times as much hydrogen. So if I had 2 nitrogen, I'm going to need 6 hydrogen. I don't have 6, I only have 4, so then the hydrogen becomes my limiting reactant. Then I just set it up to find, okay, well, with hydrogen being my limiting reactant, how much product can be formed? So I have 4 hydrogen. The ratio is 3 hydrogen for every 2 ammonia produced. And that's like 8/3, which is fine if I want to leave it as 8/3 for now. And then you kind of just have to do each one in that manner. So the second choice, for example, if I have 1 nitrogen, I'm going to need 3 hydrogen. But I actually have 5. So that's extra hydrogen. So this time, the nitrogen becomes my limiting reactant, and I just set it up then, a little mole switch, to say with my 1 nitrogen, that's the limiting, how much ammonia is produced. So I'm at 2. And then you just follow that same process for the last 2 choices. And it's going to turn out that that 8/3 mole of ammonia, that is the most of any of those 4 options. And so I think that was maybe what came easiest for me, is to look at the ratio and say, okay, I always need 3 times as much hydrogen. Do I have that? In the blue choice, I did not have as much hydrogen as I needed, so that was my limiting. In the red option, I had extra. So here's where, you could be in advanced calculus, and people will struggle with this, and it's not the mathematics. It's just the concept, the ratio. We're obsessed with ratios. How much do I have versus how much do I need? So good. Oh, it's a great question. It is annoying that you have to try all 4 choices. All right, moving on. Number 6. 7 moles of sulfur and 10 moles of oxygen are combined to form the maximum amount of sulfur trioxide. How many moles of which reactant will remain unreacted when the reaction is complete? Okay, so first of all, we have to figure out which is the excess reactant. That should narrow it down to a 50-50 guess. And then I need to figure out how much. Okay, so this ratio is a little bit funky. It's a 2 to 3. And I like it when it's a ratio I can kind of estimate in my head easily. So I'm supposed to have a little bit more oxygen. And when I look at the problem, I do. I have 7 sulfur and I do have 10 oxygen. But what if you just can't tell by inspection if that's exactly 3 to 2, or I don't know? Then you do this. Then you do this step. I don't always need this step. It's just if the ratio is kind of goofy and I can't estimate confidently. Then you pick one reactant, and it doesn't matter which. Pick moles of either reactant, and then you just do a quick mole switch. Use the ratio from the balanced equation to figure out how much of the other reactant you need. So I randomly picked the sulfur, so I'm calculating the amount of oxygen that I need. And we are actually really close to the 2 to 3 ratio, but not quite perfect. I need 10.5 moles of oxygen, but I only have 10. So oxygen will end up being my limiting reactant, which means then that sulfur is in excess. So automatically I know that one of the last 2 choices is right. Sulfur is my excess. So then I have to figure out how much sulfur do I need? How much sulfur am I going to use? And then I can subtract from the amount that I have. So I took my limiting reactant, and you go back to the amount that you really have, because that 10.5, that's what we need. We don't have that. We only have 10 moles of oxygen. I just set up a little mole switch using the ratio from my balanced equation, and then I can calculate the amount of sulfur needed. So I need about 6.66 moles, but I have 7. So I should have about a third of a mole excess. That's really, really meaty chemistry. It's such good chemistry. If you can do that, you can do anything in a free response. In a free response, they just give you funky numbers, or they'll have you convert it to grams instead of leaving it in moles. But this is like the heart of limiting reactions. It's the heart of chemistry. And the last couple. I have 78 grams of aluminum oxide, and how nice, hydroxide. They gave me the molar mass to be 78 grams. So I have 1 mole of aluminum hydroxide. It reacts with 49 grams of sulfuric acid. The molar mass is about 98, so I have half a mole. 16 grams of water were collected. What is the percent yield? Okay, so percent yield is actual over theoretical. The actual comes from lab data. How much was actually collected? If we're not running the lab, then they have to tell us the actual. That'll be the 16 grams that were collected. The theoretical is calculated using stoichiometry. If we were in the lab and we were running this reaction, everyone would calculate the same theoretical yield, but we would have different actual yields based on our lab data and any errors that may have occurred. Okay, so I have 1 mole of aluminum hydroxide, and I have half a mole of sulfuric acid. But right away, I can look at the balanced equation and say it's supposed to be a 2-to-3 ratio. I'm supposed to have more sulfuric acid. I need more sulfuric acid, and I have less. So right away, I can tell you that the sulfuric acid is my limiting reactant. So I can start with a half a mole of H2SO4. If it's already in moles, then I can cancel moles right away. Switch it to moles of water. That's the product that we collected. And then I'll cancel moles of water and switch it to grams. This ends up being half a mole times 2 times 18, which is just 18. That's our theoretical yield. And so from there, I can pick the only answer that seems reasonable. Obviously, it's not 111%. That would mean that I have contaminated water. It's not 50%, and it's not 2/3. So that 88.8 seems most reasonable. Again, I didn't have to plug it in my calculator. There's only one choice that even makes sense. Nice. All right, then the last 3, 8, 9, and 10. So somebody graphed the amount of precipitate formed as they varied the amount of silver nitrate and potassium chromate. The solutions were combined at various ratios. The precipitate formed was filtered, dried, and masked, and graphed. At what point was the stoichiometric ratio reached? So the stoichiometric ratio should be my most productive ratio. That should be the ratio where I have the most product formed. And that then should be point C. That's an easy one, right? Same with this guy then. At what point was silver nitrate the excess reactant? Okay, so we said that point C was the stoichiometric ratio, which should be somewhere in here. So it's maybe supposed to be like 30, I don't know, maybe like approximately 32 I'm going to assume that these are milliliters since it's solutions. Probably 32 milliliters of the silver nitrate. And I don't know, maybe like 17-ish milliliters of the potassium chromate. I just kind of estimate in there. And so then if I am anything over 32 grams of silver nitrate, then the silver nitrate is in excess. So that would be point D on my graph. So anywhere in this region, the silver nitrate is my excess reactant. And then by process of elimination, the potassium chromate is limiting. Anything in this region where I've got more than about 17 milliliters of potassium chromate, then my potassium chromate is the excess. And on that front part of the graph, then the silver nitrate is limiting. I'll put that in there too. The AgNO3 is the limiting reactant, and here it would be the potassium. That's my limiting reactant. So the key is to find the peak. Find the peak because the most productive ratio should represent the stoichiometric ratio in the balanced equation. And then finally, if we were collecting some precipitate, we should be able to discuss reasonable sources of error. A chemistry student is filtering and drying a precipitate that formed from two solutions reacting. Which one is most likely true about the percent yield for this reaction? Oh yeah, so improper filtering would decrease the percent yield, meaning that if you filtered improperly, you probably either left some of the precipitate behind in the beaker, or maybe you overflowed like your filtration apparatus or funnel and you lost some of your precipitate or you spilled it on the table. Improper filtering usually causes a decrease in percent yield. Insufficient drying would cause an increase in percent yield. It just then would mean that my precipitate is not fully dry and the mass would be higher than we want it to be.